we're here. We're trying to get here. Here's the dimensions, and then we also have running speed, which is when we're running on the land, and then swimming speed, which would be this distance. So we don't know whether, we should make a diagonal line from here to here or here to here. That's what we're trying to optimize. We need a variable to help us make that optimization happen. So let's call this distance x. X is the distance that we run. Okay. And then the swimming distance is going to be determined by the Pythagorean side, or not the Pythagorean, the hypotenuse side of this right triangle using the Pythagorean theorem. Right? Because if this is x, then this little space over here is going to be 5 minus x. Because together, these add to make 5 miles. And now we can use the Pythagorean theorem to give us an expression for this diagonal side over here. Let me see. Will that help us? Yeah, because then we can write an equation for the total distance we have to travel, and then we'll minimize that based on the speeds that we have. Okay. So our goal is to get things in terms of variables. That way we have something to minimize with calculus. So I've got to find out what this diagonal hypotenuse side is. So it's 1 squared plus 5 minus x squared. And that equals c squared, that unknown side. So I can expand by writing that parentheses next to itself and multiplying. If you do that, you should get 25 minus 10x minus x squared. Or actually, we don't even have to do this. We could just square root both sides. This is c squared. So this would be c. Take a square root of both sides. So c is going to be the square root of 1 plus 5. 5 minus x squared. Okay, so we're trying to minimize time, and the time depends on how far we travel. So the time function depends on this x variable. The time depends on the amount of time we spend running, which this is the distance, and then we have miles per hour. Here, look, in this classic equation, distance equals rate times time, right? If you want to solve for time, the amount of time you spend doing something is the distance divided by the rate. So I've got the time here, I'll write it out in words. Our time function is going to be the time spent running plus the time spent swimming. So we have that in terms of x. The time spent running is d divided by r. So the distance that we run is x, and the rate that we're running is 6 miles per hour. So there's our distance spent running. And now the distance spent swimming, the time spent swimming is this, the square root of 1 plus 5 minus x squared. That's our distance. And then we want to divide that by the time spent running. By the rate that we run at. Man, I keep mixing up my words in this problem. But it's d over r, right? That's the total time we spent running. That's the total time we spent swimming. And so this is what we want to optimize. We want to take a derivative and set it equal to 0, because every time we take a derivative and set it equal to 0, we find all the possible maxes and mins. So the derivative of this term is just 1/6. The derivative of this term, the 1/2 power comes down and multiplies. So that's going to make another 1/6, because 1/2 times 1/3 makes 1/6. And then this is 1 plus 5 minus x squared, and now it's to the negative 1/2 power because of the power rule. The 1/2 came down and multiplied, and it got reduced by 1. But we're not done with the derivative yet. We need to take a derivative of the innermost function. So the derivative of 1 plus parentheses 5 minus x squared, that's going to be 2. Here, I got to move this over. Okay, there we go. Now it's to the -1/2 power. Okay, so I'm still working on this derivative. I need to multiply by the derivative of the innermost function. So the derivative of this is going to be 2 times 5 minus x to the 1 power, but then times -1. Because the derivative of all this, the 1 goes away, we take a derivative. The 2 comes down, multiplies to make 2 minus 5x. And then the derivative of the next innermost function is -1. We need to use the chain rule twice there. So there's our derivative. We're going to set it equal to 0 next. And while I do that, I'm going to clean up the second term. This is all in the numerator. So we'll put 2 parentheses 5 minus x. And let's just make that a -2 because it's multiplied by -1. That's in the numerator. The denominator, because it's a negative power, we're going to move that downstairs. Okay. I think I've got everything. That's in the denominator now. That's in the numerator like it should be. We just rewrote it. So there's a derivative. Set it equal to 0 and solve to find all the potential critical points. You also want to note that any places where the derivative fails to exist is also a place that's a critical point. So x equals 5 is a critical point. We need to analyze. Oh, wait, no, it isn't. No, because that won't cause a divide by 0 error. Never mind. Any number you plug in for x will work in here because you won't get a square root of a negative. So my next step is I'm going to multiply everything by 6 times 1 plus all that stuff, because that's going to make this crazy denominator cancel out and get it out of the denominator. Yeah, we want to do that. Okay, so if we do that, that makes 0 over here, which is nice. We do that over here, the 1, 6, and the 6 cancels out. And then here, we cancel out the denominator by design, so that's -2 parentheses 5 minus x. And I'm going to add this 2 parentheses 5 minus x to both sides. Actually, let's do that. Go with this in the numerator. I mean, not in the numerator. Wow, my brain isn't working too good today. I'm not talking about a numerator. I'm thinking about top of the page. Numerator is the top of a fraction, not a top of a page. Okay, that's where we're at when we're trying to find critical points. So I add that to both sides because now I'm going to square both sides to get rid of the square root. Actually, before I do that, let's distribute. No, I'll keep it. We'll square both sides. Because if you do that, you have to square each number over here. 2 squared and 5 minus x squared. That's not 5 squared minus x squared, right? Got to square the whole parentheses. And we use the square to cancel out a square root. Now we're all set in this case because it's the reverse that would be a problem. You're only going to get positive numbers out of here, so you don't need the plus or minus symbol. Okay, getting closer. Now trying to see if we can avoid expanding those parentheses. I don't know if we can avoid it. Yeah, we can. Here, because look, I'm going to subtract 5 minus x squared from both sides because these are like terms. There's 4 5 minus x squared over here. There's 1 5 minus x squared over here. So that gives us 3 parentheses 5 minus x squared on the left side. So if I'm trying to get x by itself, I'm going to divide that 3 from both sides. Now here's where I need a plus or minus symbol because I'm using a square root to cancel out a squared. And then if I subtract that 5 from both sides, I'm going to have a negative x equals negative 5 plus or minus the square root of 1/3. Or if you divide by -1, then x is positive 5 plus or minus the square root of 1/3. Okay, so we want to check both points to see if they're maxes or mins. So I'm going to use decimal equivalents just to make it easier, but we'll probably want to type the exact answer, whether it's the plus or the minus. So 1/3, if I square root that and add that to 5, here's one of my decimal answers. I want to go back and plug this into the original function, which I've since deleted, but you probably have on your paper. I think I remember we're trying to maximize t of x, so I'm trying to maximize the time function. So if I plug that in, I gotta write it out. The distance, the time we spent running was the distance running divided by 6. And the distance we spent swimming was this complicated thing. Was it 6 or 3 over here? It was 3. We had a 6 because of when we were taking the derivative. Okay, so I'm plugging this into t of x to see what I get. Square that. Plus 1. And then the square root. Divide by 3. And then we had 1/3 square root plus 5. Okay, so that's x divided by 6 plus that other term. So I plugged the 5 plus square root of 1/3. I got 1.3144. And so we want to try what happens if we plug in 5 minus square root of 1/3. So let's get that decimal equivalent. 1/3 square root 5 minus that value. Okay, so that's what I'm going to want to plug in everywhere. So 5 subtracted by that value, square it, add it to 1, and take the square root, divide that by 3. So 0.3849 for the right term. So I got 1.12 for the left term. So it looks like this one is our maximum, because the only potential maxes or mins can happen at the critical points or at the end points. Sorry, we're minimizing that distance, right? Because we're trying to save as much running as we can. This is the correct answer, 1.122 miles, or the exact answer could be written like this. Or it's 5 minus 1 over square root of 3 is another way of rewriting that. That's the minimum distance it would take. The minimum distance that you would, that's the distance you want, I should say here. That's the distance you want to run to minimize the time. Okay, you want to run that many miles on land and then swim the rest of the way.